In this video, I'm going to be discuss about introduction to characterization and measurement of properties and X-ray diffraction with reference to metals. So, in introduction, characterization when used in material science refers to the broad and general process by which the material structure and properties are probed and measured. It is a fundamental process in the field of material science without which no specific understanding of engineering materials could be found out. The scope of the term often differs. Some definitions limit the terms used to techniques which study the microscopic structure and properties of materials, while others use the terms to refer to any material analysis process, including macroscopic techniques such as mechanical testing, thermal analysis, and density calculation. The scale of the structures observed in materials characterization ranges from angstroms, such as in the imaging of individual atoms and chemical bonds, up to centimeters, such as in the imaging of coarse grain structure in metals. Many characterization techniques have been practiced for centuries, such as basic optical microscopy. New techniques and methodologies are constantly emerging. In particular, the advent of the electron microscope and secondary ion mass spectrometry in the 20th century has revolutionized the field, allowing the imaging and analysis of structures and composition on much smaller scales than was previously possible, leading to a huge increase in the level of understanding as to why different materials show different properties and behaviors. So, more recently, atomic force microscopy has further increased the maximum possible resolution for analysis of certain samples in last 30 years. Characterization techniques most widely used in three types, that is a macroscopic testing techniques, microscopy, electron microscopy, and spectroscopy, that is X-ray diffraction technique. X-ray diffraction with reference to metals. X-ray diffraction means XRD is a powerful non-destructive techniques for characterizing crystalline materials. It provides information on structures, phases, preferred crystal orientation, that is a texture, and other structural parameters such as average grain size, crystallinity, strain, and crystal defects. X-ray diffraction peaks are produced by constructive interference of monochromatic beam of X-rays scattered at specific angles from each set of lattice planes in a sample. The peak intensities are determined by the distribution of atoms within the lattice. Consequently, the X-ray diffraction pattern is the fingerprint of periodic atomic arrangement in a given material. So Maxwell Law and Company in 1912 discovered that crystalline substances act as a three-dimensional diffraction gratings for X-ray wavelengths similar to the spacing of planes in crystal lattice. X-ray diffraction is now a common technique for the study of crystal structures and atomic spacing. X-ray diffraction is based on the constructive interface of monochromatic X-rays and a crystalline sample. These X-rays are generated by a cathode ray tube filtered to produce monochromatic radiation, collimated to concentrate and directed towards the sample. The interaction of incident rays with the sample produces constructive interface, and a diffracted ray, when condition satisfied, breaks law. So this is a Bragg's law, n lambda is equal to 2d sine theta. So in this Bragg's law, n is an integer, lambda is the wavelength of the X-rays, small d is the interplanar spacing generating the diffraction, and theta is the diffraction angle. These laws relates the wavelength of electromagnetic radiation to the diffraction angle and the lattice spacing in a crystalline sample. These diffracted X-rays are then detected, processed, and counted. By scanning the sample through a range of two theta angles, all possible diffraction directions of the lattice should be attained due to the random orientation of the powdered material. Conversion of the diffraction peaks to d-spacing allows identification of the compound because each compound has a set of unique d-spacing. Typically, this is achieved by comparison of d-spacing with standard reference patterns. X-ray diffractometers consist of the three basic elements, that is X-ray tube. So this is the X-ray tube. X-ray is developed. Okay, a sample holder. So this is a sample holder. X-ray will be diffract from here to here. This is a analyzing crystal material, and at two theta angles, X-ray detector is here. So detect the X-ray and show the image of the material. X-rays are generated in a cathode ray tube by hitting a filament to produce electrons, accelerating the electrons towards the target by applying a voltage and bombarding the target material with electrons. So when electrons have sufficient energy to dislodge inertial electrons of the target material, characteristic X-ray spectra are produced. These spectra consist of several components, the most common being Ka and Kb. K consists in part of Ka1 and K2, and K1 has a slightly shorter wavelength and twice the intensity of Ka2. So this is the anode, and these are the X-ray beams. Okay, here cathode, focusing cup, filament, and this is a target material. The specific wavelengths are characteristic of the target material. Filtering by foils or crystal monochromators is required to produce monochromatic X-rays needed for diffraction. So here K1 and K2 are sufficiently close in wavelength such that a weighted average of the two is used. Copper is the most common target material for single crystal diffraction. These X-rays collimated and directed onto the sample. As the sample and detector are rotated, the intensity of the reflected X-ray is recorded. When the geometry of the incident X-ray impinging the sample satisfies Bragg's law, constructive interference occurs and a peak in intensity appears. A detector records and processes this X-ray signal and converts the signal to a count rate, which is then output to a device such as a printer or a computer monitor. The geometry of an X-ray diffractometer is such that the sample rotates in the path of the collimated X-ray beam at an angle theta, while the X-ray detector is mounted on the arm to collect the diffracted X-rays and rotates at an angle of 2 theta. The instrument used to maintain the angle and rotate the sample is termed as goniometer. For typical powder patterns, data are collected at 2 theta from 5 to 70 angles that are present in the X-ray scan. X-ray powder diffraction is most widely used for the identification of unknown crystalline materials. Determination of unknown solid is critical to studies in geology, environmental science, material science, engineering, and biology. Other applications include characterization of crystalline materials, identification of fine-grained minerals such as clays and mixed layer clays that are difficult to determine optically, determination of unit cell dimensions. So with specified techniques, X-ray diffraction XRD can be used to determine crystal structures by using Rietveld refinement, determine modal amounts of minerals, that is quantitative analysis, characterize thin film samples and make textural measurements such as the orientation of grains in a polycrystalline sample. Thank you very much for watching this video.